Hello, 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 and welcome back to Shiksha DaCosta. Today we are going to learn how to apply the primary trig ratios. We're going to see where those apply in real life, and we're also, by the end of this, hopefully you will be able to solve problems that arise from real-world applications by using the primary trig ratios, as well as solve problems that involve two right triangles, as long as that's just in two dimensions. We're not going to go to 3D just yet. To start off, think about this question. If a plane is heading north, so let me draw this little plane over here. It's heading north at a speed of 300 kilometers an hour. So I'm just going to draw a line that shows it's sort of going straight up at 300 kilometers an hour. And then there's a 50 kilometer per hour wind that comes from the east. So if this is north, this would be east. And so the wind would be coming from here, going in this direction. Notice I drew the arrow much smaller because 50 is a lot smaller compared to 300. So this is like the sort of the speed of the airplane. We might call that a vector. And over here is another vector. It's a much less powerful vector. This is the wind coming from the east. Now, obviously, this wind is going to push the plane off course. And we have to figure out, well, what is the heading that the plane should fly at in order to compensate for this wind pushing it off its course? In other words, the plane should try its best to sort of fly in this direction to compensate. And that way, if it goes in this direction and the wind pushes it this way, well, hopefully it'll remain right on track. Our job is to find out what is that angle that the plane needs to turn so that it ends up exactly where it intended to the whole time, going straight north. Well, to do a question like this, I hope you notice that this is a right triangle. This right here is exactly 90 degrees because the wind was coming from the east and north meet at a 90-degree angle. This is a right triangle. If this is the angle in question, then this side would be the opposite side, this side would be adjacent side, and this side would be the hypotenuse. And if we want to find out what this angle is, we know that this side is 300. We know that this side is 50, so we have the opposite, we have the adjacent. That tells us to use tan. The tan ratio is equal to opposite over adjacent. So I'm going to ask you to pause the video here and see if you can figure out what that angle is. Well, hopefully you realize that, well, if the opposite is 50 and the adjacent side is 300, all we need to do is isolate theta. And the way we do that is we use the inverse operation for tan, which is just called tan inverse. Inverse operations always cancel each other out, but whatever we do to one side, we do have to do to the other side. And so the value of theta will be found by putting all of this into our calculator. And that tells us that it's about 9.462 degrees. And so the plane should turn about 9.46 degrees towards the east in order to compensate for the wind coming from the east to push it back on course. So hopefully you could see by this example that trigonometry is useful for rotating an object in by some degrees, and we can usually make a right triangle model in order to help ourselves solve that problem by imagining a right triangle over it. Take a look at some more situations where we might see right triangles appear in real life. So where would we use this stuff in the real world? For example, if you were making your own card game, like Klaus. Klaus is making his own card game, and the boxes that he ordered to keep all of his cards in are 9 centimeters wide and 4 centimeters tall. But the cards that he makes are actually a little bit bigger. They're 9 centimeters by 6 centimeters. So that extra little 2 centimeters is going to stick out of the box if he puts all of the cards in there. And obviously, he's not a fan of that, right? So what Klaus decides to do is he puts them in at an angle. So he creates this little triangular block and he puts this at the back of the box, and then all the cards can lie at an angle so they're not as tall. And that's sort of what that looks like, right? So here's the triangular block. You can see that the cards, even though the card is 6 centimeters wide, that 6 centimeters is at an angle
and the height of this wooden block is 4 centimeters. So we can actually put that wooden block right over here at the back of his box. And so it will fit the height of the box. The cards will all fit because they'll be at an angle. But the problem is, Klaus now needs to know what is the angle that he should cut his block at. What is this angle supposed to be? So that the top of the cards is actually at the top of the box and not sticking out like this. Trig ratios can help us solve problems like this. So in this case, we're looking to find out what is theta. What is this angle? Now we know that the side opposite it is 4 centimeters. We know that the hypotenuse is 6 centimeters. So there is a ratio that we can use that relates these three variables, and that is the sine ratio. Remember, the sine ratio will always tell you what is the opposite divided by the hypotenuse for any angle. So sine theta is opposite over hypotenuse, and I know that the opposite side is 4 centimeters. The hypotenuse is 6 centimeters. How does that help me find out what theta itself is? Well, we're actually going to get into this after we take this up, but after we summarize these concepts. But for every operation, there's always an inverse operation. And the primary trig ratios have inverse operations, and that's what they look like. Again, we'll go into more detail in that in just a minute. And what this does is, just like the inverse of multiplication is division, and just like the inverse of addition is subtraction, these two will cancel each other out, just like multiplication would cancel out division. And now we're left with theta all by itself. We just have to do the same thing to the other side, right? Because whatever you do to one side of an equation, you have to do to the other. And now we will find out that on the left side, theta is just by itself. And if you were to put this into a calculator, remember the calculator knows that, okay, if the ratio is 4 and 4 over 6, and we're talking about the sine ratio, then there's only one angle that could create this. And that angle, your calculator will tell you, is about 41.81 degrees, or about 42 degrees. So that's helpful for Klaus, right? He knows I can cut my block of wood at a 42-degree angle down here, and that way the hypotenuse, or this side of the block, will be 6 centimeters, so the card will fit perfectly, and this side will be 4 centimeters, so the block of wood will fit perfectly inside his box of his card game, Heroes of Tirana.
The right triangles appear all over the world in all sorts of walks of life, from choosing directions to using geometry. And if you can imagine a right triangle present in that situation, then you can use the primary trig ratios to find out any of the unknown angles or any of the side lengths. Again, as long as you have three of the other elements. When I say elements, I mean angles or side lengths. And because we're talking about right triangles, we can include that 90-degree angle as one of the three. So you only need two more. Other situations which might call for a right triangle might be elevation. And in this case, you need to know two more terms. An angle of elevation is an angle that is between a horizontal line and a line that is pointed above it. So this would be the angle that would be created. Imagine you were looking straight and you elevated what you were looking at. So to elevate means to go up. Then where are you looking at right now? How much did you rotate the direction you were pointing in? That's called an angle of elevation. And an angle of depression, very similarly, is if you were looking straight and then you turned to look down below whatever you were looking at. Well, how much did you turn? What is that angle? That's called an angle of depression. And we'll see a few examples of that.
At what angle, theta, should a carpenter cut the wooden beam below, this one right here, to shape it so that they can create a roof truss? And let's round that to the nearest tenth. So we're trying to find out what is this angle over here, because it's the same one over here, and the carpenter needs to cut it to be able to have this wood beam support the roof properly. So what I can do is I can make a triangle here. I can make a triangle going from here down here, and then all the way across to here. And I know the measurements of this triangle, right? I know that the height of this triangle is 4.3 and the width is, notice this roof is split into half. So if the full roof is 6.4 meters wide, half of it will be 3.2 meters, just divided by 2. And now that I know the side lengths of this triangle, I can use them, or the ratio between them, to find out what is this angle. I'm going to use tan because I have the side opposite this angle, and I have the side that is adjacent to the angle. I don't have the hypotenuse, so I can't use sine, I can't use cosine, I have to use tan. So tan of that angle is going to equal 4.3 divided by 3.2, which is about 1.34375. So that is the ratio between these two. The next thing I can do is I can say, okay, well, I want to get rid of tan just to get, I want theta all by itself. That's what I'm trying to find out. So I'll do the inverse tan operation, which will cancel it out. And then I do the inverse to the right side as well. And that tells me that theta is equal to 53.343 degrees. And of course, I need to round this to the nearest tenth, which is 1 decimal place. And so that would just be 53.3 because the next number is less than 5.
In this example, we see that a helicopter is hovering 500 meters above a long straight road. So I'm just going to draw that right now. 500 meters above, that's its height. Ahead of the helicopter on the road are two trucks, truck A and truck B. The angles of depression of the two trucks from the helicopter are 60 degrees and 20 degrees. Now remember, an angle of depression is, imagine the helicopter was looking straight horizontally and we rotated to look downwards. That's the angle of depression, and that angle should be 20 degrees. So from the helicopter, if we look straight at this truck B, the angle that we have created between that line of sight and the horizontal is 20 degrees. And very similarly to the other truck, it's 60 degrees. So just like that, that angle would be 60 degrees. We can use this information to find out how far apart these two trucks are to the nearest meter. If you'd like, you can pause the video here and see if you can figure that out for yourself. All right, well, this question is pretty tricky, mostly because, just for my benefit, I like to imagine triangles with the base on the bottom. And what I mean by that is, let's say, if we're looking at this truck, if I want to find out the distance between these two trucks, I can find out, well, how far is this truck from where the helicopter would be on the ground? What's this distance right here? And if you notice these three lines, well, they create a triangle. And I can do the same thing with this truck. How far is it from the helicopter? So over here, 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 that's another triangle. And both of them are right angled triangles because the helicopter, we're measuring straight down into the ground, right? That's how we measure height, perpendicularly to the ground. Okay, well, if I have this triangle here, I know that this is 90 degrees. I know that this is 500 meters, but that's only two pieces of information. I need a third if I'm going to solve it. And the third one can be found by looking at this angle here and saying, okay, well, if this is 60 degrees and this is horizontal, which is, parallel to this road, which is also horizontal, then the angle from here all the way to here must be 90 degrees. And if this portion is 60, the remainder must be 30 degrees. Together, these two would make 90. Very similarly, for this truck, this is 20 degrees, and so the remainder must be 70 degrees. Okay? And now that I have that, now I actually have in this triangle two measurements. I have an angle up here, and I have this side here, which is the adjacent side to the angle. And now I just need to calculate the opposite side. So to do that, what ratio combines the opposite and the adjacent? It's got to be tan. Tan is opposite over adjacent. And if I wanted to find out the opposite, I need to isolate that. So I need to get rid of this adjacent, and I would multiply both sides by that number. And that would leave the opposite isolated. I have the same exact type of triangle over here, right? Where the upper angle here is 70 degrees. This side is still 500, that's the adjacent side, and I need to find the opposite length, which is all the way over here. So let's look at this triangle here first. This will tell me the distance to truck A, this distance right here. We know that the upper angle is 30 degrees. This is 500. And so the adjacent side, which is 500, times tan of 30 gives me 288.675. And there's many decimals after this. And I'm not going to round this number. I'm just going to hold my calculator holds it in its memory, or if I want, I can use the exact expression as well when I'm doing any further calculations. And then I need to find out, okay, if this truck is 288.675 meters away, how far is truck B from here? And I can use a very similar triangle, except the angle up here, of course, is 70 degrees. And so 500 times tan of 70 is 1,373.738 meters. And of course, there's more decimals after that as well. But I'm just going to take 500 times tan 70, and I'm going to subtract from that 500 times tan 30. And that way I've used the exact expressions instead of rounding it. And that should give me my actual distance between these two trucks, which is 1,085.06. And again, there's many, many more decimals, but I'm going to round it to the nearest meter, and that is 1,085 meters. So hopefully from this example, you saw that, even in the situation like this, where it didn't seem like it, we could create right triangles. In this case, we needed to create two right triangles in order and subtract their side lengths in order to find that the distance between these two trucks is 1,085 meters. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.